Hello, my name is Soumyan Rajagopalan, founder and CTO of Thalia Design Automation. In today's presentation, I'll be talking about why analog IP reuse is a big problem faced by a number of semiconductor companies. I'll also be talking about the need to understand the process technology differences and how it impacts efficient analog IP reuse. I'll go over a case study and then about who Thalia are and our value proposition. What you see here is a classic decision fork faced by a number of semiconductor companies. Design new IPs or build a portfolio of analog IPs. Building a portfolio of analog IPs, what that means is designing IPs in different technologies and nodes. Obviously, both the approaches have their own advantages and needs. Designing new IPs facilitate addressing new sections of the market. New IPs demand a lot higher revenues, and it is exciting to designers to work on newer, exciting applications. Portfolio of IPs, obviously you get to expand in within an existing market, stabilizes the revenue, and stabilizes and increases the revenue. So what we are able to see from this is it's not an either or situation. How can a company address both designing new IPs and building a portfolio, given that there are opportunity costs and also shortage of capable design resources? When you look at analog circuit design, you see that it is impacted by a number of factors ranging from device performance, process technology characteristics, market needs, and finally the design methodology deployed within design companies. So this essentially makes moving a design, reusing IP, almost a redesign. So even a band gap is no longer just a tweak, but it's more of a redesign. Add to this that there are limited usable solutions in the marketplace and a shortage of good analog circuit designers. So this actually makes a difficult problem worse. So hence this begs the question, is efficient analog IP reuse a myth or a dream? Following up from the previous slide about analog IP reuse, whether it is a myth or a dream, now let us look at a case study. This case study revolves around an audio amplifier, a whisper trigger amplifier, which was migrated from 40 to 22 nanometer technology. This is a four-stage amplifier with comparators at the end, which connect to a DSP. So the key application here is power savings within SoC, largely by putting the ADC to sleep and activating it only when there is voice detected. That's primarily the application of this audio amplifier here. Now, let's with regards to the case study here, it will encompass the circuit and process technology differences and hence the issues the design teams face when migrating IP. So I will talk about it and then I'll go over the deployment of Thalia's IP reuse platform and how this was leveraged to identify the root cause of the design issues and hence the kind of solutions required. This we obviously incorporated topology changes, so I'll talk about it. And finally, I'll go over the process deployed by Thalia in getting to a solution and the delivery of the IP. Part of the effort of migrating an IP from one technology to another is qualifying the IP in the target technology. So what you see here is one of the key specification, gain max, of the amplifiers. So the picture on the right shows that the gain max slopes downward over temperature. And when you look at the box on the bottom left, you see that The gain max specification ranges from 2 all the way to 16 over corners. What this means is the circuit has not met the requirements in the target technology. And that is a problem. If the blocks, the individual amplifiers don't meet the requirement, the circuit is not functional in the target technology. And this needs to be addressed. Part of the problem is because of the MOS transistors in these amplifiers being in triode rather than being in saturation. Now, let's look at how we went about identifying what caused these problems, what process technology characteristics caused these transistors to be in triode rather than in saturation, and how we went about addressing it. What we saw in the previous slide was that one of the key specification gain was not being met in the target technology. And it was because some of the devices were in the triode region, and we needed to see what the process technology characteristic was pushing the MOS transistors into triode region. Amalia Technology Analyzer is one of the components within the Amalia IP reuse platform. This capability takes a design-centric approach, and this is deployed to analyze, compare base and target technologies to see how similar or dissimilar the process technologies are. We look at first-order effects like FTs, GMO-ID, VD-SATs, VDS IDS curves, and also second-order effects. Using this capability technology, we were able to see that the target technology here, the 22 nanometer, as far as the VD-SAT was concerned, it was very different to the base technology, and that was the reason why the MOS transistors were moving into the triode region. We'll look into the differences more in detail in the next slide. So what we saw in the earlier slides was that the devices, some of the transistors were in triode region, and in the previous slide I introduced the Amalia Technology Analyzer and the effort that happens to when comparing and analyzing the target and base technology. So what you see on this screen is a subset of the kind of analysis we perform. And there are the key specifications, the key technology characteristics are listed here. As you can see here, the VTs are similar. However, the VD-SAT min between the base and target technology, the difference is about 5x. What this means is, when you look at GM over ID at specific VD-SAT points of 70 volts and 200 millivolts, what is clear is in the base technology, you can operate the device at closer to 70 millivolts because the VD-SAT min is 0.036, 36 millivolts. While in the case of the target technology, you can't operate the device at 70 millivolts, largely because the min VD-SAT is 1.556, which means that you need to operate it closer to the last row here. So as you can see here, GM over ID in the first case is closer to 13.58 because of the VD-SAT min, while for the target technology, it is closer to about 8.5 or so because of the VD-SAT min. What this means is, for a given ID, you have lower GM in the target technology, and to achieve the same GM, you need to pump in more ID. So essentially, this is the root cause of the problem why the transistors were moving into triode region in the target technology. And we have to, the solution here is to recover the lost VD-SAT so that you can have higher gain. So I'll talk about the topologies in the next slide. So what we saw in the previous slide was that the VD-SAT between the base and the target technology were different by an order of about 5x. Obviously, this difference was the reason why the devices went into the triode region rather than being in saturation. So the topology is listed on the screen. There are three. They're essentially put together to recover the lost headroom. I won't go into the detail on the functionality of these topologies, but the motive was to the motivation was to recover the lost headroom. The key thing, the key mantra here is because of deploying the Amalia technology analyzer, we were able to accurately estimate the reasons, the root cause for the circuit to fail in the target technology, and we were able to address the right solution to make sure that the circuit works in the target technology. Our philosophy at Thalia is that targeted design automation works. Full-on automation is difficult and near impossible in analog circuit design. What you see on the screen are snapshots of the automation that was deployed during different processes, various different steps when migrating the circuit from the base technology to the target technology. What you see here are the circuit characteristics after the fixes to the topology. So what you see at the bottom left is that the circuit now meets the requirement across all corners. And the picture on the right shows that the curves for gain is now almost flat. The range of gain max variation over temperature is now very narrow. So what this means is the circuit now works in the target technology. As part of this IP reuse engagement, we were able to deliver both the schematics, the verified data, and the layout. I founded Thalia back in 2011. The primary motivation was to improve the overall efficiency and hence, and in the process, reduce the cost of analog circuit design, primarily to roll out a unique analog IP reuse platform. The last several years, we have partnered with few IP vendors, and we have deployed our capability in numerous foundries and nodes. We are headquartered in the UK with design centers in Germany and India. Why are we unique? At Thalia, we are bringing about a paradigm shift in the way analog IPs are reused. We have rolled out a unique platform called Amalia IP Reuse Platform. And this is a combination of proprietary technology, methodology, and design capability. This platform, this combination is what we call the trifecta. The technology consists of automation capability, AIs, and software engineering, design expertise. Obviously, aspects of analog circuit design can only be handled by capable designers, and methodology is knowing where you can deploy automation and where the expertise could come into play. This is our trifecta. There are four key value propositions that we bring to the table. The first is using our platform, supporting our customers in IP migration. This is moving IPs from one technology, process technology, or node to another. The second is generating a portfolio of IPs, i.e. creating different flavors. For example, designing different load current LDOs or different jitters or different frequencies in a DC-DC converter jitter for a PLL. The third value proposition is IP improvement, specifically targeting performance, power, and area, which is something that all IP vendors would like in their IP, something better than the competition. And the fourth value proposition is delivering process technology analysis to customers. So this comes into play when customers would like to qualify and compare new technologies, process technologies against existing process technologies their IPs are on. So this is something that we have delivered successfully to a number of customers. The Amalia IP reuse platform consists of technology, methodology, and design expertise. On the technology and methodology front, the platform has four components. The technology analyzer, this is something I covered when I went over the case study. In a nutshell, this is a design-centric approach that addresses key first order and second order effect of process technologies, extracts and compares between the base and target technology to provide the user with clear inputs on how similar the technologies are, the base and target. Um, Automated circuit porting, this effectively takes in the inputs from the technology analyzer and generates a circuit that could then be verified depending on how close the circuit's functionality is, circuit's responses in the target technology. We then deploy the design enabler along with design expertise, and we nudge the design back into specification. And finally, layout migration. This capability is about putting together the base layout framework, which is then expanded by experienced layout designers. At Thalia, we have a track record of working on applications ranging from baseband all the way to RF front-end applications. So what you see on the screen are examples of design reduction to the design cycle time that we were able to bring on customers' design. We are partners of choice with multiple IP vendors in Europe, and what you see here are time savings up to about 50% on applications ranging from PMIX all the way to Wi-Fi IP. And what you see on the screen is one of our partners. So we've worked on a number of Wi-Fi's and Bluetooth IPs, and we have delivered silicon validated solutions to this customer. And as you can see here, there is an acknowledgement of reduction to the design cycle time and improvement to efficiency that we have brought to their design flow. To recap, at Thalia, we are bringing about a paradigm shift in the way analog IPs are reused. This is through Thalia's unique IP reuse platform called Amalia, which is a combination of proprietary technology, methodology, and design expertise. We have a track record of working on applications ranging from baseband all the way to RF front-end applications. We've delivered reduction in design cycle time up to 50%, and in the process, reduction to the cost of reusing IPs as well. We have a proven track record of working on a number of nodes and technologies, and we are happy to help you. So if you would like more information about how Thalia can help you in more efficiently reusing your IPs, please get in touch with us. Thanks for your time.